Recall that in the previous video we defined a basis set as a set consisting of three non-coplanar vectors which can generate all the vectors in 3D space as their linear combination, and that too for any given vector in 3D space it is a linear combination of basis vectors in a unique way. The scalars that appear as coefficients in such a linear combination are unique for a given vector. Now this is what the author next has to say about basis sets. In applications involving the cross product of vectors, we are yet to see this operation, but actually I think you already know what cross product of vectors is, of two vectors. That is also sometimes called the vector product of two vectors. To define this thing, the distinction between right and left-handed basis sets matters. Now what is this right and left-handedness? There is, let's see what the author has to say. There is no experiment in classical mechanics or electromagnetism that can distinguish between right and left-handed sets. It's a fact. So that is why the difference can only be exhibited by a model or some familiar object that has a handedness, such as a corkscrew. Now you can see in the text that a general right-handed set of vectors has been defined using a corkscrew, which is a little complicated. We, however, luckily won't need that, because we will mostly be interested in handedness of special type of basis sets, that is orthonormal basis sets. Recall that a set of vectors, of three vectors actually, is called an orthonormal set of vectors or an orthonormal basis if all the vectors are unit vectors, they all have magnitude 1 and they are mutually perpendicular. That is, if you take any two distinct vectors from that set, then their directions are perpendicular to each other. So for such a basis set, let us see what right-handedness means. So the author gives this example of a right-handed orthonormal basis set consisting of these three vectors I, j and k. And you can of course understand that this is a house and one corner of the house has been chosen as the origin. And from that origin, that is taking that origin as the initial point, we have these three vectors. Why is it an orthonormal basis set? Let us first see that. All the vectors are unit vectors. They all have magnitude 1. Okay. So that is why normal. Okay. Normality means having vectors of magnitude 1. And where is this ortho coming from? Orthogonal means being perpendicular. If you look at one corner of a room, you need not go outside. Wherever you are right now, you see in one corner, three lines are emanating from that corner which are mutually perpendicular. You take any two of them, the angle between them is 90 degrees. So that is why orthonormal basis. And why will this be a basis set? That is because these are non-coplanar vectors. You cannot translate them parallel to themselves in any way so that ultimately the translated vectors lie in one plane. That will never happen for these three vectors, and that is why they are able to generate all the vectors in three-dimensional space that we saw in the previous video. So that is why they form an orthonormal basis set. Now what about this right-handedness? What does it have to do with the right hand? Well, note that the vectors have been written in a particular order, I followed by j followed by k. What happens is this, you can understand right-handedness like this. Really what is happening is, you cannot see it in this diagram, but you do understand that j is actually not like this, but I is like this, j is like this, and k is like this. So you follow the order, say you start from I, okay. So this is your I and this is your j. Now if you take your right hand and curl the fingers except the thumb, then the fingers are curling in a way that you are going from I to J. Okay, you are rotating from I to J, then the thumb should point in that direction in which the third vector is pointing. If that happens, this is I, this is J, and this is K. If the fingers curl from I to J, the thumb should point in that direction. If that order is being maintained, then that basis set is right-handed. There is another way of recognizing a right-handed basis set. You can point your right hand fingers like this, okay, thumb, index finger and middle finger, so that they are mutually perpendicular. And I want you to do this. You try to imagine how you can orient your hand so that your index will point in the, actually I can show it like this, but it's a bit inconvenient for me. I points in that direction, J points in that direction, and K points in this direction. Index, middle, thumb. Okay, so that is the right-handed set. Whereas if you encounter a set in which, say, you imagine this same thing, that is curling fingers, that is more convenient to think of. Say you curl your fingers in such a way that you go from the first vector to the second vector. Okay, but you see that this is not the direction in which the third vector is pointing, but it's in the other direction. Then it will be a left-handed set, because then that direction will be achieved by your left hand. You can try to imagine these things, okay, but you do get the point what a right-handed basis set is. Next we have definition 1.6 of a standard basis set, or in short a standard basis. If an orthonormal basis is also right-handed, then it's called a standard basis. If it is left-handed, then we won't call it a standard basis, although it may still be an orthonormal set. Oh, and there is one more thing I forgot to mention totally. Actually, I should have done it when defining unit vectors. You do not see the usual arrowhead, right, above these vectors. Instead, you are seeing a wedge type of symbol like this. That symbol indicates that the vectors are unit vectors. And we read this notation like this: I hat. Okay. Next we have position vectors and vector geometry, and in this part we are going to set up a one-to-one correspondence between all the points in three-dimensional space and all the abstract vectors. Let us see how. Suppose O is a fixed point in space. So we pick any arbitrary point in space and we fix it. Okay, we are not going to change it in this discussion. So this is O. Then relative to the origin O, relative to O as the origin and an underlying frame of reference. This part is not exactly clear right now, but it will be clear at some point. Okay. So you just think of O. We have chosen O, we have fixed it, now it's not going to change. Now relative to this O as the origin, any point A in space, say this is my A, O and this is A, has an associated line segment OA. We have written line segment here, or rather I should say the author has just simply written line segment, but actually he means directed line segment in this context, obviously. OA, which represents some abstract vector A, some abstract vector whose magnitude is equal to the length of the line segment OA and whose direction is from O to A. Conversely, the vector A is sufficient to specify the position of that point capital A. How? Well, you already know that abstract vector A has many geometric representations as directed line segments. Precisely one geometric representation starts from O, and the O is the initial point and the terminal point is that point A. So this way we have set up a one-to-one correspondence between two sets. One set has all the points in 3D space and the other set is the set of all abstract vectors. And based on this discussion, we next have definition 1.7 of position vector. The vector A, that is this vector A, is called the position vector of the point capital A relative to the origin O. So the position vector of a point A in space relative to a fixed origin O is that abstract vector which the geometric vector OA represents. And using this idea, in the next video we are going to prove some geometric facts which you already know, some theorems from Euclidean geometry which you proved when you were in school, but that time you proved these things using only geometry, geometric tools, axioms from geometry. Now, however, with the help of this idea of position vector, we will see that we can prove those same things much more easily.